another test now. We're going to do the same test for independent samples. We'll do the same test for independent samples, except this time we got a slightly different group of data here. We got two machines. We get output from the two machines. This is machine one. This is the amount of production you get out of machine one. This amount of production you get machine type two, different machines, different factories, but of different type, one type or another type, two types. Okay, I'm going to analyze the differences to find the average output. Again, analyze, compare means, independent samples t-test, right? Except this time, I'm looking at the output, the average output for the two machines. I'm going to put in the machine type and the grouping variable. Again, I got to tell it it's 1 and 2. It's already in there from the last time we did this. Okay, you got to move out the old data, move in the new data so that it realizes that it's comparing the machines, not the recipes. And I'm going to click OK. Okay, let's see what my output looks like this time. Okay, well now, machine type 1 had an average output of 23. Machine type 2 had an average output of 20.5. Is the mean between in those two samples big enough to say that the mean difference for all of machine type 1 is different than the average for all of machine type 2, the population of each type of machine? Okay, this time, let's take a look at what our, first thing we got to do is take a look, see if our variances can be considered equal or different. We start off with the assumption that equal variances, that these have equal variances, and we're going to use this top line. What's the probability of being wrong if we reject that hypothesis, that the variances are equal? Well, the significance of probability of being wrong if I reject that hypothesis is 0.01, is 1.6%. So, do I reject the null hypothesis that the variances are equal and use the second line, not equal, or do I stick with the first line and say equal or not equal? Opinions. Okay, let's get an opinion. Equal or unequal? These variances are equal or unequal? I know you're out there. I can see there's people out there. Oh, I got two opinions here. Okay, we say that you don't know. Okay, we got a couple that don't know. Okay, let's see. Okay, this significance represents the probability that you would be wrong if you reject the null hypothesis. In other words, that the variances are equal right here. The probability that you would be wrong if you reject that null hypothesis is less than 5%. It's only 0.01, right? So since this number is less than 5%, you say that this is wrong. I reject the null hypothesis and use equal variances not assumed instead. So we would say that because this is less than 5%, we're not going to use the top line. We're going to use the second line. Okay, guys, comfortable with that? See why I say that? It's always got to be the same every time you see one of these two-lined boxes like this. Okay, so now let's figure out from here what the t-scores. Notice the results are pretty similar, right? Degrees of freedom are a little bit different, significance are a little bit different, but they're similar results. The t-score for the difference between the mean for machine type 1 and machine for t-type 2 is a t-score of 1.355. Still not very large, right? Okay, what's the probability of now the hypothesis that this part from this line to the right, this all tests for the equality of the means for population of machine 1 and population of machine 2. Okay, well, the t-test tells me that the difference in t-score between these two means is 1.355. That doesn't look very likely to me to be sufficient to reject the null hypothesis and saying that machine 1, the mean for machine 1 is equal to the mean for machine 2, right? So if I look at this, I say to myself, okay, that's what the t-score is. This is degrees of freedom. What did SPSS calculate as the probability that I can reject the null hypothesis and not be wrong? Well, 19.8, right? 19.8% chance of being wrong if we say that these two means are different. We reject the null hypothesis that they're the same and reject that and say that they're different. I have a 20% chance almost of being wrong. I know my tolerance, my alpha error, my tolerance for alpha error is only 5%. So do I reject the null hypothesis because of this result, or accept the null hypothesis, or fail to reject the null hypothesis? Reject or fail to reject? Opinions? Fail to reject. I like that. That's good. Everybody agree that's fail to reject? Because that number has to be less than 0.05 for me to reject the null hypothesis that the mean for machine 1 equals the machine for machine the mean for machine 2. Okay, it also does another 95% confidence interval. Notice in this one that 0 is within the 95% confidence interval for the difference, and it's in there. So you can't say that the difference between the two averages are different. So you get the same result as we just got. You fail to reject because you can't say that the difference is different than 0. Okay, so now another situation that we might run into is, let's go back to our data here. Another situation that we might run into is paired data. Okay, so here is a couple of columns of paired data before and after. What we're saying here is for subject number 1, that we measured them before some intervention. Okay, let's say we're testing blood sugar and we're using a drug that affects blood sugar. We tested patient number 1, we tested before they took the drug, and we tested them after they've been on the drug for a week. Patient number 2, tested them before they took the drug and after they've been on the drug. Okay, notice that this is not data for one group of people that didn't take the drug, that didn't take the drug versus another group of people that did take the drug. This is the same person before and after. So really, to look at the effect of this drug, we're now looking at the difference between what happened to blood sugar for the person before they took it and after they took it, right? So we're really looking at the difference here between these two groups. And we can do that because it's really the same person. See, if this were two different people, one taking the drug, not taking the drug, we couldn't just subtract one's value from the other. We would have to just look at it as normal independent samples, the way we did the previous two examples. So in this case, since they're paired, since it's from the same person, say before and after, right? We can look at this as paired data, okay? And it helps us to analyze this a lot more efficiently because we can look at the difference between these. This person went down 13. This person went down 9. This person went down so much. This person went up 4. This person went, down so much. So I can look at it as a series of differences instead. So I'm going to go to Analyze. I'm going to go to Compare Means, except this time we go to Paired Sample t-test. Remember, we did one sample t-test, independent sample t-test, which could be equal variances or unequal variances, and paired sample t-test. Okay, so now in this case, I'm going to move stuff back here. This is where you'll see it. So in this case, it's going to wait for you to tell it two variables. Which is the variable before, which is the variable after, or which are the two columns that I'm comparing. So I'm going to move before in here and after in here, and it matches the two of them up. It realizes that this is really the same person before and after. Okay, if you want another set of variables, machine 1 and machine 2, you could put them in. It has to be formatted that way. You use this data in two columns. Most of this stuff is not formatted in two columns. That's why you don't see it before and after. So I'm going to click OK, and it's going to compare the differences between these two. Okay, let's see what kind of table I get now. Okay, here's the output that I get. Okay, my sample size is 16 people, 16 patients. Okay, it does a correlation and so on and so forth. Here's the average before was 211. The average after was 201. It does the whole thing with sample size count and so on and so forth. There were 32 measurements, but only 16 pairs of measurements. Okay, there's a correlation that it does. We're not really concerned about that right now. But we come down here to our paired samples t-test. Okay, and it's taking the differences between the two of them and looking for the average difference. The average of all the differences, if we made a third column and calculated all the differences, the average for the differences between the blood sugar before and blood sugar after is 10.5. The standard deviation for the differences is 11.5. The standard error, because it's a sample size of 16, we divide that by square root of 16, which is 4, so it comes out to be a little under 3, right? Standard error is about 3. So now it calculates, well, the difference in the means is 10. The standard error is 3, so the z-score, right? The z-score or the t-score for this, because only sample size is 16, right, is going to be equal to 3.6. That's 10.52 divided by 2.89 is going to give you your 3.64, just the way you would calculate it manually for a single sample t-test. Okay, it almost treats these paired samples as if it's a single sample t-test, and you're testing the hypothesis that the mean difference is equal to 0 or the mean difference is not equal to 0. Okay, so let's see which of those two mean. Our null hypothesis is that the average difference between before and after is equal to 0. We actually found an average of it being 10, but we want to know if that's a big enough difference in t-values for us to reject the null hypothesis that the differences between those two are not 0. Okay, so here's our t-score. Our t-score is 3.6. I'm feeling a lot better, even though it's not a big sample size, and our degrees of freedom are only 15, right? What's the probability of getting that big a difference if the differences are equal to 0, if the null hypothesis is true? The probability of that happening is that'll only come up less than 1% of the time, 0.002 or 0.2%. So my probability of being wrong if I reject the null hypothesis is less than 1%. Do I reject the null hypothesis, or do I fail to reject the null hypothesis? Opinions, please. Reject or fail to reject? We reject it. This is less than 0.05. Thank you. I think we're unanimous this time. Right, exactly. It's less than 0.05. So we reject the null hypothesis that the difference between the mean difference between before and after is equal to 0, and we accept the alternative hypothesis that the difference between these two averages is not equal to 0. We accept the alternative hypothesis. Okay, good. So that's basically the kind of thing that you're going to run into here. Okay, and I think that if you keep these general rules, I'm gonna post the formulas later on, but if you keep these general rules in mind, if you unfortunately were to have to do an actual calculation manually, I'll post those. It's a pretty tedious calculation, but you're really just filling in numbers then. Okay? You'll see the formulas. It'll tell you the means, the standard deviations, and so on and so forth. If you're told it's equal variances, you'll use one formula. If you're told unequal variances, you use a different formula. If you're told it's equal variances, you'll determine the degrees of freedom one way. If you're told it's unequal variances, you'll determine the degrees of freedom using a different formula. Okay, so I'll post those for you later on so you can use them for references, or you can just bring in your book. They're in the book. Okay, so that's what we're after here. Okay, and I'll also post these later on when I get the videos up. I'm gonna post these later on, and I'm gonna point out to you that, for instance, here, that if this value is less than 0.05, use the second line. If this value, and in this case you reject the hypothesis that they're equal variance, so you use the second line because it's smaller than 0.05. So I'm going to point out to you that, well, now if this value, the significance, is less than 0.05, you reject the null hypothesis and accept the alternative. But if it's not less than 0.05, you fail to reject the null hypothesis. I'll make up a little note that if you just key in on that and look for that. So along with the videos, by sometime probably tonight or early tomorrow morning, I'll have that posted as well, so you can use that kind of for reference. And I'll do it for the other tables as well. Okay, like for instance this table. This table over here, this is for paired samples. Well, for paired samples, here's our mean difference. Our null hypothesis is that the mean of the differences is equal to 0. or the alternative mean of the differences is not equal to 0, right? This says the mean of the differences is 10. Is that, can we reject the null hypothesis is that the mean of the differences of the means is 0? Well, we go over here, we see a t-score, and we see 0.002, and we know that if this is greater, if this is 0.05 or greater, we fail to reject the null hypothesis. If this is less than 0.05, we reject the null hypothesis. So in this case, we reject the null hypothesis. Okay, so I'll try and post some of these tables so that when you go back into SPSS and practice a couple of these with SPSS, track down some of your own data, just type in your own numbers and stuff like that, and just get comfortable with using it. So when you're doing the exam, yeah, I'll post the answer. By the way, somebody asked me about the answers homework 5. I'll get those up by tomorrow morning also. If when you're doing the exam, when you're working on the exam, that you don't have to flub around a lot. If you practice a little bit before using SPSS, which just sets the data, even numbers that you make up yourself, just getting familiar with the menus and the selections and the choices that you can use, that you can select. If you do that a little bit in advance, when you're doing the exam, you're going to be that much more comfortable. That's one less thing you have to worry about because you kind of have an idea where things are. So you can concentrate on the answers to the problem rather than having to spend a lot of mental energy on where is this, where do I find this in SPSS, because you'll be a little bit more comfortable with it. So practice makes perfect on any of this kind of stuff.